As displayed on the screen, I will cover 3 topics today. Let's begin with the brief introduction of DNA methylation. DNA methylation is a common epigenetic modification, with the signature 5-methylcytosine being well known. DNA methylation also involved in many biological functions, such as gene expression and tissue differentiation. It also plays critical roles in many diseases, such as cancer and age-related disease. Currently, sodium bisulfite treatment is a common method for DNA methylation analysis. However, such a method is not compatible with the UNG PCR system. As we know, UNG is commonly used in molecular labs to prevent PCR carryover contamination. So let me explain the reasons behind the incompatibility. The methylated cytosine indicates as green. Unmethylated cytosine bases indicates as dark gray. After bisulfite treatment, unmethylated cytosine bases are converted to uracil, whereas methylated cytosine remains unaffected. During PCR amplification, when without UNG, uracil bases are converted to thymine. However, with UNG will digest U-containing DNA fragments, therefore no PCR amplification occurs. So an alternative approach we propose here is to apply methylation-sensitive restriction enzymes treatment, then followed by digital PCR detection. Let me introduce the concept of methylation-sensitive restriction enzymes and digital PCR. Methylation-sensitive restriction enzymes are used to analyze the methylation status of cytosine in CpG sequences. As their name implies, only selectively digest unmethylated CpGs, then leaving methylated cytosine intact. There are many commercially available enzymes, each of them with distinct cutting sites. Now let's introduce the state-of-the-art technology known as digital PCR. Digital PCR allows absolute quantification through partitioning the reaction. Partitioning is the step of dividing the sample into many thousands of nanoliter scale reactions. After PCR amplification, endpoint contain positive and negative partitions based on the fluorescence signal. The concentration determined by Poisson statistics. So what are the benefits of using digital PCR, especially in the context of DNA methylation analysis? First of all, digital PCR allows absolute quantification without relying on standards, which is beneficial for any PCR assay that requires for quantification. Digital PCR also enhances precision through subsampling the sample into many thousands of reactions, therefore improving the reproducibility and accuracy. Increased sensitivity and reduced competition are achieved by concentrating the effective samples through partitioning. Also, digital PCR has better tolerance to inhibitors due to endpoint detection and partition. Let me walk you through the workflow. Begin with the sample preparation. This step will involve enzyme treatment, followed by PCR reaction setup, supplement with high GC enhancers. I will get into this process shortly. Then proceed partitioning and endpoint data collection. In addition, Roche Digital LightCycler offers a unique combination of features that will maximize the flexibility for DNA methylation analysis. During PCR reaction setup, 5 times concentrated DNA master mix allows high sample volume input that maximizes sample utilization. We offer 3 types of nanowell plates, and that will maximize the flexibility for your application. For example, we have multiple partitioning options and multiple sample volume input options. The analyzer integrates PCR amplification and data collection. 6 optical channels will open up a high level of multiplex capability. Now let's explore the 3 types of nanowell plates. On the top is a high sensitivity plates, which offers 20,000 partitions with a filling volume of 45 microliter. In the middle is a universal plates, which offers 28,000 partitions with a filling volume of 30 microliter. At the bottom is a high-resolution plates, which equipped 100,000 partitions with a filling volume of 15 microliter. Those 3 types of nanowell plates open up a realm of possibilities for various applications. To your right is the data shows the total valid partitions obtained from those 3 nanowell plates. I need some pointing. In the middle, you can see the high sensitivity plates, and on the between the little bit over 2,000 partitions, that's a universal plates, and on the top is a high resolution plates, as well as in the first lane is a Bio-Rad QX200 system, which indicates as a green color. So those data were collected from multiple rounds with various sample types. So notably, Digital LightCycler system consistently yields a high number of valid partitions. And this consistency will ensure the reliability and the reproducibility. Finally, let's go to DNA methylation analysis. The target of interest in this study is the RAS family 1 isoform A promoter. The methylation of RASF1A promoter has gained much attention due to its increased frequency in many cancer types. CpG islands extend in the promoter and the exon regions. Primers and probes are designed specifically targeting promoter. Unfortunately, there was an unexpected challenge happened during the preliminary testing, and I only detect 30% of quantification compared to the expected concentration when testing healthy human genomic DNA, and only achieved 15% when testing methylated DNA positive control. So after a while troubleshooting, it was discovered that the problem was stemmed from the high GC content in CpG regions, causing inefficient PCR amplification. So next step, to overcome this challenge, several high GC enhancers were applied. The data shows here was showing the impact on quantification with various high GC enhancers at different concentrations. A healthy human genomic DNA and methylated DNA positive control were measured here without enzyme treatment. As we observed, no GC enhancers, the quantification results is not match expected concentration. By adding 5% DMSO, 7.5% DMSO, as well as 7.5% glycerol, and high GC enhancer from AEB, it significantly improves the accuracy of quantification. with expected concentrations falling within 95% confidence intervals. To the right, it's the 1D clustering shows the 1D clustering results with different concentration of DMSO. So in line with the quantification results to the left, you will see the positive clustering, the density is visibly changed while applying different concentration of DMSO. And when supplement 10% DMSO is starting to interfere the performance. The blue lines in the bottom, that says negative partitions, while the red color indicates positive. After solving the problem of high GC bias, let's look at the digital PCR detection results. The restriction enzyme we used in this study is HHA1. The multiplex digital PCR assay developed, including target gene and 2 reference genes for the purpose of digestion completion control and import correction control. Dashed lines and solid lines show the location of enzyme within the amplicon region. Notably, there are no enzyme cutting site on reference 2. The 1D clustering on the right. Healthy human genomic DNA and methylated DNA were both measured before and after enzyme digestion. After enzyme digestion, we observed only a few positive partitions left on the RAS-F1A promoter region when testing healthy human genomic DNA. However, those are strong positive observed on the methylated DNA positive control. As you may notice, actin serves as digestion completion control. It demonstrates almost complete digestion when testing healthy human genomic DNA. However, there's a strong positive showing the methylated DNA. This is because this methylated DNA positive control was obtained from enzymatic conversion. So we anticipate the presence of undigested amplicons. EIF serves as input correction control, so it's always ready for amplification. The next question, how we calculate the methylation fraction. Here is an example. 2D clustering from target gene and input correction control, both before and after enzyme digestion. So first step, to calculate the ratio between the reference gene, between the target gene to the reference gene. So we got the 2 ratios here, both before and after enzyme digestion. Second step, to comparing the ratio after digestion to the ratio before digestion times 100. That is the number you will get for the fraction. So the methylation of this example is 97%. We have here 3D clustering obtained from 3 fluorescent channels. On the left is 3D clustering of methylated DNA positive control after enzyme digestion. On the right is 3D clustering of healthy human genome DNA after enzyme digestion. So you can see there are distinct visual difference in the clustering patterns by comparison the positive and the negative samples. And each group of clustering are color-coded. So at last, we measure the methylation status in various cancer cell lines. On the left is on promoter region. So as you can see, in healthy human genomic DNA, the methylated fraction was measured around 0.7%, while there are a broad range of methylation levels was observed in cancer cell lines. Similarly, on the exon 1 region, the methylation of healthy human genomic DNA was measured less than 0.1%, while a broad range of methylation levels were observed through the different cell lines. So we also in agreement with other studies, there are variables of methylation status was observed between the promoter and the first exon. So, okay, here are some highlights for this application. Importantly, there were no observation of template loss with restricted enzyme cleavage followed by digital PCR detection. You would appreciate this method compared to the bisulfite treatment. Second, the high GC enhancers improve the accuracy of quantification. And our Roche Digital LightCycler system provides a simple workflow and superior performance. Thank you. Now I'm going to introduce Stephanie.
Thank you, Yu. That was a wonderful talk. Thank you all for being here. My name is Stephanie Barbary. I'm a research scientist at GT Molecular, and I'm really excited to share performance of our AML panel that we've developed for the Roche Digital LightCycler and its potential uses in minimal residual disease monitoring. Just a quick disclaimer, any assays that are developed at GT Molecular are research use only and are not intended for diagnostic use. Just a brief outline of my talk, I'll give an introduction to GT Molecular and tell you about who we are. And then I'll give some background to minimal residual disease and liquid biopsy. And then I'll present our AML panel comprising mutations in IDH1, IDH2, and NPM1. And then I'll showcase data from our assay on liquid biopsy samples using the Roche Digital LightCycler, and I'll finish with conclusions and next steps. So GT Molecular, we're a biotech company located in northern Colorado in the city of Fort Collins, and we specialize in digital PCR assay development, which has led to a contract with the CDC and several collaborations, including this wonderful collaboration with Roche. We really took off during the COVID pandemic with SARS-CoV-2 testing in wastewater, and we've since expanded to several other harmful pathogens that are present in wastewater, and also into the oncology space with liquid biopsy and the utility of digital PCR. So just a bit of background, I think we can all appreciate that liquid biopsy has the potential to revolutionize cancer care. Not only is it minimally invasive, but it also offers several advantages to traditional tissue biopsies. For instance, from one sample, you can capture the heterogeneity of both primary and metastatic tumors that might be present and make therapeutic decisions appropriately. Additionally, blood samples are very easy to obtain. A patient is willing to give them, and so you can collect them over time to longitudinally monitor treatment efficacy. And finally, liquid biopsies can be used to detect minimal residual disease following tumor resection or the end of treatment, and also look for any drug-resistant mutations that may arise. A little more on minimal residual disease. This refers to any cancer cells that are left after surgery or treatment. And in order to improve the longevity and quality of life for these patients, we really need an economical, sensitive, and rapid means to detect these mutations and monitor how well a treatment is working and look for any cancer recurrence. And we believe that liquid biopsy offers a perfect solution, is the perfect sample type for this because it's affordable, it's sensitive, it's non-invasive, and it's a great use for monitoring for these mutations. There are several IVD assays out there for detecting liquid biopsy monitoring, and there's also plenty of literature out there showcasing that this is a viable option for solid tumor types as well as blood cancers. So we propose that the best strategy for minimal residual disease monitoring is to identify the driver mutations using NGS, and then collect liquid biopsies and use digital PCR to detect those mutations that were identified via NGS. And you already kind of mentioned this, but for those that may not be familiar with digital PCR, we believe digital PCR is the best method for this because it's much more sensitive than other traditional PCR methods. And this is because a DNA sample that comes from the blood is going to be mostly wild-type DNA, and you're trying to find a needle in the haystack with those mutant particles that will likely be drowned out by wild-type amplification. So with digital PCR, you take a sample and you separate it out into tens to hundreds of thousands of partitions, each containing 0 or 1 to 2 molecules of DNA, and you perform endpoint amplification, and you're able to directly detect and quantify your mutant target. So a little more about the AML panel that we've developed. So AML is a cancer that originates in the bone marrow, and often therapeutic and prognostic implications or decisions are made based on their mutational profiles. And how we approach assay development for liquid biopsies is we identify those mutations that have therapeutic consequence or prognostic implications and create a multiplexed digital PCR panel accordingly. So for AML, we identified the mutations shown on the table on the right. We have NPM1, which are NPM1 insertions are one of the most common mutations in AML. They provide positive prognostic risk typically in these patients, and they may be an early marker of AML. We also have IDH1 and IDH2 mutations. These are common hotspot mutations, again, are potentially early markers of AML and also have targeted therapies. So just a little bit of background on these mutations. NPM1 is ubiquitous nucleus to cytoplasmic shuttling protein. And in mutations that occur in NPM1 are typically 4 nucleotide insertions that cause a frame shift in the C-terminal domain, affecting tryptophan residues 288 and 290. This results in a loss of a nucleolar localization signal and acquirement of a nuclear export signal. And this leads to aberrant cytoplasmic localization of mutant NPM1 and its binding partners that are involved in apoptosis, DNA repair, and differentiation, ultimately leading to uncontrolled myeloid progenitor cell growth in AML. These mutations are present in about 30% of AML patients, and these mutations are considered gatekeeper mutations in that they often co-occur with early arising mutations in IDH, DNMT3A, and FLT3 ITDs. And it's not until patients acquire these NPM1 variants that then oncogenesis is initiated. Additionally, NPM1 mutant AML has really gained a lot of attention in the spotlight lately due to its positive prognostic risk and is now considered a distinct genetic entity among WHO classification. For IDH1 and IDH2, these are metabolic enzymes that convert isocitrate to alpha-ketoglutarate. These, as I mentioned earlier, these mutations are early events in tumorigenesis. They are present in several different cancer types, including AML at about a 20% frequency and anglioma at a surprising 80% frequency in low-grade gliomas. The mutations exclusively map to arginine residues in IDH1 and 2, R132 in IDH1, and R140 and R172 in IDH2. And this makes these mutations great targets when you have those hotspot mutations for detection. These mutant enzymes convert alpha-ketoglutarate to 2-hydroxyglutarate, which is an oncometabolite that alters epigenetic regulation and ultimately leads to altered differentiation and tumorigenesis. And as I mentioned earlier, there are targeted therapy options for these patients, again, further substantiating their role in liquid biopsy and MRD detection. Monitoring of these mutations may also be beneficial for some patients. This study that was published last year of over 3,000 AML patients showed that there was co-occurrence of IDH and NPM1 mutations among all age groups. So IDH mutations are not as common in younger AML as opposed to older, but you do still see the same prevalence of about 50% of patients having both mutations. And in the same study, they showed that the co-occurrence of IDH and NPM1 in younger patients had showed superior survival compared to patients with just one IDH mutation or IDH alone, or triple mutants. So IDH with NPM1 with either FLT3 ITD or DNMT3A also had worse survival. Another great utility of using this panel in a MRD setting is looking at MRD status at the time of hematopoietic stem cell transplantation. This study was published last year as well, and where they looked at the MRD status of a patient before transplantation and compared that to either recurrence or survival. What they found was that out of 44 patients who were IDH positive at the time of diagnosis, 75% still had a detectable IDH MRD at the time of transplantation. And there was a strong association of relapse with IDH1 R132 or IDH2 R172 positivity, not the case for IDH2 R140Q, who had better or less association with relapse. Interestingly, with R140Q, most patients who were 140Q positive and NPM positive at diagnosis had cleared NPM1 at the time of transplant, and only the patient that still had NPM1 remaining relapsed. So again, just further substantiates the utility of using this panel in monitoring these mutations throughout. So now that I've told you about the utility of this assay, let's show you the data. And you did a great job explaining the Roche and how great it looks. So this is our NPM1 assay. And as I mentioned, NPM1 insertions, it's always 4 nucleotides at the same site, but those 4 nucleotides can vary among patients. So in order to develop an assay that will detect all of pretty much any insertion that occurs in one reaction, we developed a drop-off approach. So how this works, and I apologize that I don't have a pointer, but in one amplicon, you have a probe that binds at the site of the insertion, where the insertion would occur on wild-type DNA, and you have a reference probe downstream. And so in a wild-type sample, in 2D analysis, you'll get a double positive population. In the event of an insertion, you have a drop-off of that FAM probe, and you only have single positive hex population. So in a mixed sample containing mutant and wild-type DNA, your single positive hex blue population is showing your NPM1 mutant concentration. This assay in 1D shows really good, robust signal-to-noise ratio. Again, you can easily distinguish positive partitions from negative. In this, what I have up here, you have a 0.5% variant allele frequency standard, 100% wild type, and 100% mutant. You can see in the 100% wild type, you have equal output of FAM and hex, and you have a drop-off of signal in the 100% mutant. And you can see that in a more realistic sample of a 0.5% mutant, you don't see any differences in 1D. However, when you analyze this data in 2D, that's when you're able to distinguish your population. For our IDH targets, again, this is showing a 0.5% reference standard, wild type, and 100% mutant control. We see robust signal-to-noise ratio. We don't see any cross-reactivity on wild type, and we can detect really low VAFs. And the same story is true for R140Q and R172K in IDH2. Robust signal-to-noise, no cross-reactivity. And for this standard, it only had R172K, but we were able to detect the mutation in this sample. The limit of the detection for the assay performs really well among all targets. You can detect at least 0.03% VAF, and you can see that the theoretical VAF is correlated with your amount of input DNA. So if you increase your DNA even further, you could potentially reach even more greater sensitivity. And we see a good correlation between our theoretical and expected outputs for percent VAF. Additionally, this assay is compatible with DNA from all sorts of different types of matrices, including plasma, whole blood, FFPE, and bone marrow. And you can see that there's similar output for all of the targets among these different types of DNA. And last, I'll go over data from real-world samples. Unfortunately, we had a difficult time acquiring AML samples with these mutations, but we were able to get our hands on IDH mutant samples from liver and pancreatic cancer patients. So this was a 45-year-old female with stage 4 metastatic liver cancer. Her blood was drawn 20 days after diagnosis and 4 days prior to starting chemotherapy. And this is data from cell-free DNA isolated from 1 ml of plasma. So you can see that we were able to detect the variants from even just a small amount of plasma. A similar story is this patient was a 71-year-old male with stage 4 pancreatic cancer. The blood was drawn 14 days post-diagnosis and 7 days after starting systemic chemotherapy. Again, 1 ml of plasma, we were able to easily detect the mutations. And unfortunately, we didn't have time points before and after, but this would be a great example of getting a baseline of cell-free DNA levels and then seeing how those levels respond to treatment. So to conclude, I've shown that liquid biopsy provides the ideal sample type for longitudinal monitoring and minimal residual disease monitoring. And we've developed an IDH1, IDH2, NPM1 panel for the Roche Digital LightCycler and it can detect mutations from several sample types with high sensitivity and good performance. And we have several oncology assays for the Roche DLC available soon. In the coming months, we'll have one for BCR-ABL fusions that are common in chronic myeloid leukemia, as well as ESR1 aromatase inhibitor resistant mutation panel for breast cancer. And I'd like to thank my director, as well as Dr. Sarah Kane, the GTM team, Roche, and all of you guys for attending. And I hope you really enjoy the AACR while you're here. Thank you.